We just learned the method of variation of parameters for solving differential equations. Now we're going to apply that method to solve this differential equation, which describes the rate of change of the amount of salt over time inside this tank. We derived this equation in an earlier video, so let's recall that x of t is the total number of grams of salt in the tank at time t, and v of t is the total liters of fluid in the tank, which we found to be equal to 800 plus 2t. Also recall that this first term denoted the rate at which salt enters the tank, and this term denoted the rate at which salt exited the tank. We were also told that initially this tank contains fresh water, and that gives us an initial condition. We know that x at 0, so the number of grams of salt in the tank at time equals 0, is equal to 0 because there is no salt in the tank. So in this video, we will be solving this initial value problem. Before we get into solving this, we can actually make some predictions about what will happen in the long-term behavior. So we're going to make a long-time prediction. Recall that we said that the concentration of salt in the tank is equal to x of t over v of t. For us, this means x of t over 800 plus 2t. After a long time, we expect that the concentration of the fluid inside the tank is equal to the concentration of the fluid that we're continuously pouring into the tank. So that means that this expression will be approximately equal to 75 grams per liter for large T. So if we solve for x of t by multiplying both sides by this denominator, we can predict that x of t is going to be approximately 75 times 800 plus 150 t for large T. So this is our long-time prediction of the solution. And you might be wondering, well, if we know what the solution is going to look like after a long time, why are we solving this equation? Well, we wanted to make this tank habitable for fish that we would use in an experiment. And these fish live in a salt concentration of 34 grams per liter, which is not really close to 75 grams per liter. And we were looking for a specific time at which this happened. So we do need to solve the full equation in order to find out when that would be. So this looks like it might be a linear equation. And if so, we need to put it in standard form. So we're going to put it in the form x dot plus a function of time, which I'll call p of t, times x, is equal to another function of time, which I'll call q of t. In our case, if we move this term to the left-hand side, this is the same as dx dt plus 3 over 800 plus 2t times x is equal to 375, where this is p of t and this is q of t. Since q of t is not identically 0, this is an inhomogeneous equation. So we'll need to use the method of variation of parameters to solve this. So let's start with that method, and there's 4 steps. We'll start with step 1, which is to solve the associated homogeneous equation. This is simply solving the equation where the right-hand side is equal to 0. So that amounts to solving dx dt plus 3x over 800 plus 2t equals 0. This is a linear homogeneous equation, which means that it's separable. So we're going to use separation of variables. If we separate variables, we get that dx over x is equal to minus 3 dt over 800 plus 2t. Now we integrate both sides. On the left-hand side, we get natural log of x. And on the right-hand side, we can factor out a minus 3 from the numerator and a 2 from the denominator to integrate dt over 400 plus t, which gives us minus 3 halves times natural log of 400 plus t plus c1, where c1 is an arbitrary constant. So now, there's a couple things to note. First, the left-hand side should also have an arbitrary constant, but we can just subtract that from both sides and absorb it into this constant c1. Also, notice that I do not have the absolute value signs around the arguments in the natural log, and that's because we're not really interested in scenarios where those terms are less than 0. So we keep that in mind and just use parentheses. I've also written x here, but just remember that this is not the same as the x that solves the full equation. This is just for the homogeneous part. So we have natural log of x equals minus 3 halves times natural log of 400 plus t plus c1. And then we exponentiate to get that our homogeneous solution is e to the c1 times 400 plus t to the minus 3 halves. Now, for the method of variation of parameters, we only need to choose one non-zero solution to the homogeneous equation. So we're going to choose the solution where e to the c1 is equal to 1. This gives us the homogeneous solution of 400 plus t to the minus 3 halves. And notice here that I've chosen to write this as x of h because this is just one homogeneous solution. Now I'm going to rewrite this equation up on the next board, and we'll continue through step 2. Now we're going to move on to step 2 in the method of variation of parameters. We're still solving this differential equation, and in the last step, we found that this is a solution to the homogeneous equation. Now, our next step is to substitute a form of the solution x that looks like a function u of t times the solution to the homogeneous equation. We don't know what this function u of t is just yet, but we're going to make this substitution and come up with an ODE for u. We'll solve for u, and then that will give us the two pieces we need to reconstruct our solution x. So let's do that now. So substituting u times xh into this equation gives us d dt times u times x of h plus 3 over 800 plus 2t times u times x of h. And this is equal to 375, which I'm going to write on this side. So now, remember that both u and x of h depend on t, so we need to do a product rule for this term. So we get that this equals u dot times x of h, which we know is 400 plus t to the 3 halves, minus 3 halves, excuse me, plus u times the derivative of x of h, which gives us minus 3 halves times 400 plus t to the minus 5 halves, plus this term, which gives us 3 over 800 plus 2t times u times x of h, which is 400 plus t to the minus 3 halves. Now, if you simplify, you'll see that these two terms actually cancel with each other. And that's because we said that this term is x sub h dot from the product rule. And this term is x sub h. So if you factored out u from this expression, you would see that we just had u times x sub h dot plus 3 over 800 plus 2t times x sub h. But we know that x sub h satisfies the homogeneous equation, which means this is equal to 0. As a double check, you can actually make out this computation and see that these terms do indeed cancel. If they don't cancel while you're doing these computations, it means that we've made a mistake, and it was probably in the computation of x sub h. So it's good to go back and check your work in step 1. So now that these terms cancel, we're left with an ODE for u, given by the left-hand side here, is equal to this. I'm going to rewrite this so it's a little more clear. So we have that u dot is equal to, I'm going to move this term to the other side. So we get 375 times 400 plus t to the 3 halves. Now when you carry out this step to solve for u and you get an ODE, this ODE will always be separable. In our case, it's even easier because it's just an integration. So if we carry out this integration, we'll see that u of t is equal to 150 times 400 plus t to the 5 halves plus c2, where c2 is an arbitrary constant. So from step 1 and step 2, we now have both pieces that we need to find the solution to our original inhomogeneous equation. So that brings us to step 3, where we just multiply these pieces together. So step 3 tells us that x of t is equal to u of t, which we just found to be 150 times 400 plus t to the 5 halves plus an arbitrary constant. This is u times x sub h, which is 400 plus t to the minus 3 halves. Now I'm just going to distribute this term to these two terms. And we'll see that x of t is equal to, when I multiply these two terms, the exponents go to 1, and so I'm left with 60,000, which is 150 times 400, plus 150t, plus c2 times x sub h, so we get c2 over 400 plus t to the 3 halves. So this is our general solution to the differential equation. But remember, we also had an initial condition that x at time 0 is 0. So in step 4, we can apply that initial condition and that will let us determine what C2 is. So if we plug in 0, we know that x is equal to 0 at time 0. So 0 is equal to 60,000 plus 150 times 0 plus C2 over 400 to the 3 halves. And if you work out what this is, you see that C2 is equal to minus 4.8 times 10 to the 8th. So now we can put this all together and get that x of t is equal to 60,000 plus 150t minus 4.8 times 10 to the 8th over 400 plus t to the 3 halves. So this is our solution to the differential equation. But it looks a little fishy. Let's see if we can make some sense of this. So we said before, we made a long time prediction that after a long time, x of t would be approximately equal to 75 times 800 plus 150t. Well, After a very long time, t is going to be very large, and it's being raised to a power that is greater than 1. So this denominator is going to be huge as t gets huge. So this term is going to go to 0. That means that after a long time, we'll be left with this, the steady state solution, and this is called the transient. But if you carry out this multiplication, you'll see that we correctly predicted the steady state solution in our long time prediction. So now we've found the explicit expression for the amount of salt in the tank. And remember, we were thinking about the concentration because we wanted to have the tank be habitable for sea fish so that we can do our experiments. So in the next exercises, you'll carry out more analysis on this solution and find out when we'd be able to put the fish into the tank.